So let's look at.
With Morphin Explorer, can you just copy the URL over to Chrome?
I tried, and I think I did find the one, because I did try my bookmark that was in Explorer. I tried to copy it over, and I did find my one, but then it was actually, we're talking about disk method. Eventually we'll talk about washer method, and it was more about washer method. The other one I couldn't get to work at all. So, I don't know. I'll have to do some more looking and maybe get you guys another visual here. Okay, so solids of revolution, this is level 1, so to speak. I think there's maybe 3 total. We're going to do 1 and 2. Okay, so today it's disk, and that's what he was showing you, okay? It created, when he rotated the rectangle, it created a circular disk, and that's what we're looking at here. So when we are rotating disk, we're taking a region bounded by 2 values, A and B, spin it around the axis of revolution. So the one he showed you was spun around the x-axis. We'll also talk about spinning around the y-axis. Cut a slice off the solid, lay it flat. When you cut a slice off, it's a circle, right? That was the circle he was showing you. And then the radius of the slice will be equal to the function. And then, so notice what it says. The volume of the solid will be the integral from A to B of pi times f of x quantity squared dx. This is volume here, right? And the idea, we're basically using the area of a circle. If you remember area of a circle is pi r squared, right? Pi times radius squared. And so that function is replacing our radius. Okay, the function is replacing the radius. Now, let's look at our first example. I'll take you through the picture, try and show you the idea, and go from there. Okay? So example 1, ask us to find the volume. So again, when we hear area, we think integrals, right? When we hear volume, we also need to think integrals, but now we need to think about times pi and squaring the function. So not just integrating the figure, but times pi and integrating the function. So find the volume of the solid formed by revolving the region bounded by y equals negative x plus 1 and the coordinate axes, so x and y axis. And what are we revolving around? X-axis. Okay, a picture. What's y equals negative x plus 1 look like?
It goes through the y-axis at 1, and then it just goes at a slope of negative 1. So it's just decreasing across.
Okay. Y equals negative x plus 1 has a y-intercept of 1, a slope of negative 1, which is going to go down 1 over 1. So that means it's also going to cut through the x-axis at 1. And so it looks like this. It said the volume of the solid formed by revolving this region bounded by y equals negative x plus 1 and the coordinate axis around the x-axis. So what is it we're revolving? Yeah, the chunk in the first quadrant, which is just this little triangle, yes? We're going to take that triangle, and this little arrow here indicates we're going to revolve around the x-axis. Okay, so we're revolving around the x-axis, this little triangle. And this is where I struggle with drawing it, making a 3D image look good here. Can you visualize what this triangle is going to turn into if you revolve it 3D? Can you visualize a cone? Because it is a cone. And Oh, I know I did. Here, let me switch over. Was I in Chrome when I found it? Let me show you this real quick. Except, okay, is it going to come up quicker than Con did? Let's see, I think. Oh, here we go. So, okay, this triangle is backwards from our triangle. I don't think there was another one. Okay. I did forget line going the opposite direction, right? So when you rotate that around, it's rotating. There's the lower part, and it looks like this cone here. Is that what you had visualized? If not, that's what you should be visualizing, except our cone will be flipped the other way. Not that it matters, but our cone will be flipped the other way. And then when we're rotating about the x-axis, we're going to have a little slice of it, right? A little circle of it right there. We're finding the area of that and integrating. Because remember, when you integrate, you're adding up all the different slices. So, hopefully that gives you guys a little bit idea of what you're looking at. When we think about a little rectangle, because we are revolving about the x-axis, first of all, because we're revolving around the x-axis, we're going to be in terms of x. So because we're going to be in terms of x, we want a little slice there of the x, which it just represents dx. And if you remember dx represents the change in x. So it represents dx, or we've talked before about it being called delta x, right? The change in x. And so it's dx or delta x. But that's what goes around and makes the circle. Okay. So, in order to find volume, remember, what is the volume formula? Up here, off the screen, of course. It's the integral from a to b of pi times the function squared, because that's going to be your radius, dx. So can you set this one up? There's my setup for you. An integral. Okay, you should always start with a pi. And that's something you'll see, think multiple choice. What are they going to trick you with? They're going to give you the answer with pi and the answer without pi. Okay, so you can't forget the pi. Okay, what else? What is the function that's spinning around the x-axis? Negative x plus 1. So this line right here is making the outer boundary. So it's going to be negative x plus 1 quantity squared times dx times the width of that slice. And then you're looking at, on the x-axis, because it's all in terms of x in this one, the bottom of the cone is at 0. The top of the cone is at 1. So from 0 to 1. Questions on my setup?
Will we any that are spun around the origin?
No. You have to. We can only spin around a line. So we have to spin around some kind of line. So, and we'll always use vertical or horizontal lines. Today, specifically, it's X and Y axis. Okay, guys. The pi is a constant, yes? So, good practice is to put the pi out front. Times the integral from 0 to 1. What do I have to do before I integrate? Can we integrate a quantity raised to the second power very easily? No, you should be foiling it out before you integrate. So it's negative x plus 1 quantity squared, so negative x times negative x, x squared. Minus x times 1 is minus x, and another minus x is going to be minus 2x, and 1 times 1 is plus 1. You do need to do that preliminary work there. Now, can you integrate? Carry the pi down. Integral of x squared. Add 1 to the power, divide by the new power. I say 1/3 x cubed. Notice the guy in the video would have said x cubed over 3, right? Minus integral of 2x. X squared. Plus the integral of 1. Just x. Evaluated between 0 and 1. This is a good type to practice by hand, not rely on the calculator. So I'm going to keep my pi out front. And the first time through, I'm going to plug in 1. So 1/3 minus 1 plus 1. And then we're going to subtract. And now I'm going to plug in 0. 0 minus 0 plus 0. What's this all clean up to be? It's 1/3 times pi, which is pi over 3. Because it's volume, we can say units cubed. Okay, got it? The math is not crazy hard. I mean, it's integrals, the stuff we've been doing. It's just understanding the setup. Okay, let's try example 2. And ask questions when you have them, folks. Find the volume of the solid formed by revolving about the x-axis, the region bounded by the graphs y equals e to the x equals 0, x equals 1, and the x-axis. Well, drawing the graph here is half the battle. First of all, do know I'm going to be revolving around the x-axis. I like to put that little arrow just as my visual reminder. Okay, what's y equals e to the x look like? Yep, good. I heard stuff in and out of class. Exponential graph runs over here along the left, along the x-axis, has a y-intercept, cuts through at 1 and continues up, right? So we know it cuts through here at 1. And then it says x equals 0. What is the line x equals 0? That's the y-axis. What is the line x equals 1? Vertical line at 1, yes? So we've got x equals 0, x equals 1, the x-axis, y equals e to the x, so the piece we are revolving. Daryl called it a plateau. I can go with that. I mean, it's going to, as it rotates, it's going to kind of be like a cylinder, except the edges of this cylinder kind of curve out instead of being straight up and down. Does that make sense? Okay. So, again, we're rotating around x-axis. So my slice, my rectangle right here is going to be a vertical one representing dx. And of course, this was e to the x. Okay, guys, we need an integral. Okay, we're going to be working in terms of x. What are my x boundaries? 0 and 1. Because it's volume, we always have to start with a pi. And what is the function that's rotating? It's e to the x. And what do we do with that function? Square it. So the integral from 0 to 1 of pi times e to the x quantity squared dx. Well, again, I'm going to put my pi out front. From 0 to 1, what is e to the x quantity squared? When you raise a power to a power, you just multiply powers. So this is e to the 2x dx. Which is good, because if it was e to the x squared, that would be much harder to integrate. Okay, pi. What is the integral of e to the 2x? Yeah. The integral of e to some power, or derivative of e to some power, is always e to some power, but if we take the derivative, you're multiplying by 2. If you're doing the integral, you're compensating for that 2, so you're saying 1/2 e to the 2x, evaluated from 0 to 1. Now, I got a thought for you if you want. Pi is a constant already out front, yes? What's another constant that's in this problem? 1/2. Could I put that 1/2 out front and not have to mess with it? You can, and so if I put that 1/2 out front with pi, 1/2 times pi is pi over 2. And then it's e to the 2x. So e to the 2 times 1, which is e to the second, minus e to the 2 times 0, so e to the 0. What do we know about anything raised to the 0? It's 1. So pi over 2 times e to the second minus 1. And that's actually how I'm going to leave my answer. If necessary, could you come up with a decimal answer? Of course. And this is units cubed. Because again, we are talking about volume. Okay, moving along. Gotta make sure I try and get through this stuff. Example 3. If you've already started reading it, what changes? We're going around the y-axis. Okay, guys. If you're going around the x-axis, you're working in terms of x. If you're going around the y-axis, you're working in terms of y. Okay? We definitely prefer to go around the x-axis, but that's not the way it works always. So, let's look at this graph. You're always going to see me drawing a visual here. Okay, there's my x and y axis. Find the volume of the solid formed by rotating about the y-axis. I'll put my little reminder up here. The first quadrant region bounded by the line y equals 3. What's the line y equals 3? At a horizontal line that goes through the point 0, 3. So there's my horizontal line that goes through the point 0, 3. And the graph of y equals the square root of x. I just taught this in Algebra 2 last period. What's y equals the square root of x look like?
half the sideways
Half of a sideways parabola.
parabola.
So mine kind of come together there. Okay. Now, we're rotating this about the y-axis. What is the piece we're rotating?
The shaded region that's not shaded
The shaded region that's not shaded yet.
yet.
That's a good answer. I didn't shade it yet because I want you guys to tell me what to shade.
It's a triangle with an arc for its side.
Okay. So this triangularish type area here, is that what you're trying to tell me? Okay. If we're going around the x-axis, it would be a different story. But since it said going around the y-axis, it's bounded by the line, the curve, and it goes around the y-axis. Okay. In the past, we would, because we were rotating about the x-axis, we drew a section of dx. Because we're rotating about the y-axis, first of all, notice your rectangle is now perpendicular to the y-axis. And this represents dy. Okay. I had my equation here, which was y equals the square root of x. And of course, we had that x equals 3. Okay. Before we get started, we have to think in terms of y, correct? Well, you know we're probably going to have to use this. Y equals the square root of x. What is this if I say x equals? Square both sides, and x equals y squared. Because we're working in terms of y, we have to put in the y's, and so it's in x equals. We did this the other day with something, right? Okay. Now, do you see the visual here? We're taking this section and rotating it about the y. Does this remind you of the picture the guy drew in the video? Except his was sideways, right? It's kind of a cone, but like with sucked in sides. That's what we're drawing here. So, of course, we have to have pi. What's the radius? What takes me from the y-axis up here? What is the top height here? The curve, which is y equals square root of x. But what am I, if it was around the x, I'd use square root of x. Since it's around the y, we're going to use y squared. But it's y squared squared times dy. Evaluated from what to what? 0 to 3. When we work in x's, we take values from the x-axis. Because we're working in y's, we take values from the y-axis. So remember, I'm just going to put little y equals there. Those are y values. So they came from the y-axis. Now, besides that, this problem's pretty easy. I mean, in that it's basic and compare, you know, it's nothing fancy here. What do you know about y squared squared? Y to the fourth. So we're doing pi times the integral from 0 to 3 of y to the fourth dy. I feel like he already did this for you, didn't he? I've got a pi out front. What's the integral of y to the fourth? One-fifth y to the fifth. Evaluated from that fun 0 to 3. Now, you can do y to the fifth over 5 like he did. That's fine. The other option, can we go ahead and put this 1/5 with the pi? There's no right or wrong thing here. So then I'm saying pi over 5 times y to the fifth evaluated from 0 to 3. So that's going to be 3 to the fifth minus 0 to the fifth. 3 to the 5th? 243. So it's going to be 243 minus 0, so 243 times pi over 5. So I'm going to say 243 pi over 5. And of course, units cubed. Needless to say, I would have, I don't know, maybe you guys would have done okay with the video here, but I feel better teaching it in person. Okay, example 4. Got example 4 and 5 to get through. Find the volume of the solid formed by rotating about the y-axis, the first quadrant region. Notice it is often first quadrant region of the circle whose equation is x squared plus y squared equals 9. Well, specifically said first quadrant region. Yeah. And x squared plus y squared equals 9. A circle centered at 0, 0. Because it says 9, that's a radius of 3. So what's the picture we're looking at? A quarter of a circle. And that's not the best, but you get the idea. Okay? So that's the shape we're drawing. It did say rotated about the y-axis. Since it's rotated about the y-axis, obviously you figured out that it's this half or this quarter circle. What's that going to look like when we rotate that? Okay. I heard hemisphere in class. I heard a dome thing here in my ear. Okay. Maybe a bowl. Dome, hemisphere. I guess it is. It's an upside down bowl if I say bowl. But, okay. So you have a visual going. Good. Because we're going to cross the y-axis, my section is perpendicular to the y-axis, and this represents dy, right? So that represents the piece that is revolving to make that dome, that hemisphere. Now, what form do we want of the equation x squared plus y squared equals 9? We want it to be x equals. Because we're revolving about the y-axis, which means when I work the problem, I'm going to use y's in my problem. So if I solve this for x, officially, 9 minus y squared, the square root of it, and officially I should say plus or minus when I solve that, right?
In this equation, since it's only the first quadrant, wouldn't you just use the positive?
You got it. In this situation, when we solve it, we get that. But in this situation, because it's only the first quadrant, we're only using the positive version. Yep. Okay. There's my integral. Don't forget your pi. And so, rotating around the y-axis, and we rotate around the y-axis, what is that function that's rotating? What we just had there, right? So square root of 9 minus y squared. What do I have to do with the function since it's volume? Square it. Remember, pi times the function squared, dy. Evaluated from, what are my boundaries? (0 and 3). And notice I circled the 0 and 3 on the y-axis because I cannot stress enough, working with y, use y's. Okay, I'm going to pull the 9 out from 0 to 3. What's nice about this? What do you get when you square the square root?
9 minus y squared.
Yeah, 9 minus y squared times dy. Okay, so pi out front. The integral of 9 is 9y minus the integral of y squared, y cubed over 3, or 1/3 y cubed, evaluated from 0 to 3. Gotta love all these zeros we've been getting today. Okay, pi. And then the first thing I'm going to do is I'm going to plug in a 3. 9 times 3 is 27, minus 3 cubed is 27, divided by 3 is 9. And we're going to subtract, and the next time we plug in 0, which is just 0 minus 0. 27 minus 9 is going to make this 18 pi units cubed. Okay. One last one. And a good one to talk about because instead of giving us a number, they use K. We've had something like this in homework not too long ago that we talked about with a K. Find the volume of the solid formed by rotating about the, oh hey, we get to go back to x-axis. The region bounded above by the circle, whose equation, x squared plus y squared equals k squared, and below the x-axis. Well, what is that?
That's a half circle. Are we getting out of the first quadrant?
Okay, so this is a circle centered at 0, 0 with radius of k. It said find the volume of the solid formed by rotating about the x-axis, the region bounded above by the circle, and below by the x-axis. Did it specify first quadrant? It did not. So we are using, oh gosh, that's horrible. Yikes. I have to show that to you? Ugh. Okay. That is horrible. Ignore. But radius of k means this intersection point over here is positive k. This intersection point over here is negative k. And this intersection point up here is k. Obviously not drawn to scale. We were told to rotate about the x-axis. Okay, so we are rotating this whole half circle. When you rotate a half circle three-dimensionally, what's this going to be? A sphere. Okay, so we're going to have a sphere. Now, rotating about the x-axis means we're back to having our slice being dx. Rotating about the x-axis, what do I want my equation to be in terms of? We're going to solve it because I want to show you that's what it equals. So, because we're going to be in terms of x, we want this to be solved in terms of x. So, officially it's y equals plus or minus the square root of k squared minus x squared. But again, we're only going to need the positive half, correct? Okay. The integral. Pi times my function squared, so the square root of k squared minus x squared, quantity squared, dx Okay. So, and I'm running out of time. So, evaluate from negative k to positive k. Technically, what else could you do instead? Multiply it by 2 and just go from the 0 to k? Because if my figure was drawn appropriately, it would be symmetric. Okay. So, I'm going to pull the pi out front. Pi times the integral from negative k to positive k. What happens when we square that square root? K squared minus x squared dx. Remember, k is a number, right? So when I say, what's the integral of k squared? K is a number. So when we do the integral, it's going to be k squared x minus, what's the integral of x squared? One-third x cubed. Evaluate from negative k to positive k. Okay. Pi out front. The first time through, I'm putting in k. K squared times k is going to be k cubed minus 1/3 times k to the third is going to be 1/3 k cubed. In parentheses, minus, begin the next parenthesis. This time, I'm not putting 0 in, so I actually have to do it this time. I'm going to put in negative k. K squared times negative k, negative k cubed, minus 1/3 times negative k to the third, which is really going to become plus 1/3 k cubed. If I do some cleanup, my first parenthesis, 1 minus 1/3 is going to be 2/3 k cubed, minus, over here it's negative 1 plus 1/3, which is going to be negative 2/3 k cubed. 2/3 k cubed minus negative 2/3 k cubed is going to become 4/3 times the pi that's out front, 4/3 k cubed. What does k represent? The radius. What's the volume of a sphere? 4/3 pi r cubed. What's the volume of our figure? 4/3 pi k cubed. So yes, if you realize that geometrically, you know, I've talked about how AP likes to make you think about these things geometrically. Could you jump there? Yes, you can. Now, for my purposes today, I wanted to just work it out. I wanted you to see that, yes, it really does work out to be the volume of a sphere formula. Okay? But recognize that geometric connection. They like to use circles and portions of circles. Okay? Okay, so I guess this means tonight your homework is 71. You'll just have to maybe skip the problems to go with 70. Tomorrow, no virtual, my 3 boys at home. Daryl and Vincent, go to the library. I'll have a sign up on the door if you forget. There'll be a video for 70. It's actually already posted. And homework for 70. And I guess we'll be checking like 3 assignments come Monday. Lovely. Gotta love those days.